Hello, good morning friends. Yesterday we have seen how to handle the boundary conditions for a given structure and how to reduce the size of the global stiffness matrix and then how to solve the linear equations to get the displacement vector. So today we will continue with certain numericals where I actually demonstrate you how exactly the problems on FEM will be solved. So let us take one simple first problem. If this is, for example, this is the first problem where there are three stepped bars. This is the first step bar with a larger diameter. Then the next diameter is going to be smaller than that. Then there is going to be the smallest, which is going to come here, and the other end is also fixed here. So this is one thing. Here there are two loads. Here I have given a 20 kilonewton load is applied at this particular point, and here a 10 kilonewton load is applied at this point. The area for this A1 is 900 millimeter square, and the G or the E, what you can say E1, is 70 gigapascal. Similarly, the area A2 for this is 400 millimeter square and 105 gigapascal is the Young's modulus for this. And the last one is the smallest member with 200 millimeter square, and being steel, this is going to be 200 GPa. Now let us take the lengths of each of these members. These are the L1, L2, L3 of these three members. First one is 80 mm, second one is 90 mm, and the third one is again 70 mm. So we need to solve the various displacements. The things to be found out are nodal displacements, and second one is stress, and third one is the reaction if possible. So we can show these are the three important things what we have to see here. To start with, first always we have to write down the element stiffness matrix. First let us model this. So once we model this, this will be a three element member with like this, having four nodes, four global nodes, 1, 2, 3, 4. This is the first element, second element, and the third element. And the displacements here are Q1, Q2, Q3, and Q4. And the corresponding forces here are F1, F2, F3, and F4. So these are the four forces which are to be applied at the four nodes, and the corresponding nodal displacement vector is going to be Q1 to Q4. So first let us write the element stiffness matrix. Element stiffness matrix for the first member. See, in general we know that K for a particular element is given by AE LE upon EE into bracket. This is going to be AE EE upon LE, 1 minus 1 minus 1 1. This is the general form of we can say the element stiffness matrix, and let us write it for element number 1. For element number 1, let us write the stiffness matrix, element stiffness matrix as 1. Area is given 900, then 70 into 10 raised to 3 is going to be the Young's modulus, and the length of this member is 80, and this is going to be 1 minus 1 minus 1 1. When you multiply this and when you convert this, what we are going to get, this is 10 raised to 5 into bracket 7.875 minus 7.875 minus 7.875 and 7.875. Look at the connectivity. Obviously, this is 1, 2 for the first element. Maybe if you want a connectivity table also, you can put it here. If you take this table like this, then you write this as element number, and these are the local node numbers 1, 2. So 1, 2, 3 element, it is 1, 2, 2, 3 and 3, 4. This is going to be the element connectivity for all the 3 elements. So let us write this as 1 and 2. This is 1 and 2. Let us write this for element number 1. Now let us write for element number 2 now. Here it is going to be K2, where the area is going to be 400 into 105 into 10 raised to 3 is going to be the Young's modulus, and the length is going to be 90. So this is 1 minus 1 minus 1, 1. This will give me answer of 10 raised to 5 into bracket 5.714 minus 5.714 minus 5.714, 5.714. So if you take the connectivity, it is for the second element it is 2 and 3. We are going to take the element connectivity for the second element. Now similarly in the similar fashion, you can write it for element number 3 also. Element 3. This is K3, which is equal to 200 is the area, 200 into 10 raised to 3 being the Young's modulus, and the area length of this member is 70. So 1 minus 1 minus 1, 1. This again gives you a total of 4.667 minus 4.667 minus 4.667, 4.667. This is for the element number 2, and for the third element it is going to be 5.714 minus 5.714 minus 5.714 and 5.714. So naturally this is having the connectivity 3, 4 and 3, 4. So since the total number of the global degrees of freedom are 4, our global stiffness matrix size is going to be 4 by 4. So now let us go for global stiffness matrix. Global stiffness matrix. If you write like this, this is the capital K. This is going to be called as global stiffness matrix. So if we write this here, this K is given by, it is going to be 1, 2, 3 and 4. This is going to be again here 1, 2, 3 and 4. This is going to be the element connectivity for the global stiffness matrix. So one by one, if you start entering into this, it will become 7.785 minus 7.785. Here it will be 0, 0 minus 7.785. Here there is a summation between node 2 being common. It is going to be 12.542. These things are getting added because this one is getting added with this. So these two are getting added and the total sum is going to be 12.542. And remaining is as usual 6670. Here you will have 2 zeros and 1 zero here, minus 4.667. Here again at node 3, you look here, this part is getting added with this. So these two are going to be appearing in 3, 3 and the 10.381 and minus 5.714 minus 0.714, and this is going to be the last 71.4. So once you have completed the global stiffness matrix, now let us write the load vector, because there are two loads which have been given here. So we need to consider those load vector. So therefore, let me write this load vector. See the load vector, global load vector I am telling, of course global load vector, which is called global F. See here, since there are no loads at node 1, I will put it as node 1, whereas there is a load at node 2, there is a load at node 3, and there is no load at fourth load. So 1, 2, 3, 4, if I write this, this is going to be my, whatever you can say, the global load vector. Now once we know that, we are already aware that the FEM equation for solving this is going to be, the FEM equation is always going to be KQ is equal to F. So first let us write this, and then later on we substitute the boundary condition, and using one of the methods, let us say this problem we will solve it by elimination approach first. We will solve one or two problems on elimination approach first, and then we will take numericals on penalty approach. So therefore, if I rewrite this, of course here we have forgotten, this is the 10 raised to 5, should not be forgotten. This should be always there on the outside. So now let me rewrite this 10 raised to 5. Once again we will write 7.785 minus 7.785, 0, 0, minus 7.785, 0 and 0, 12.542, minus 4.667, and finally 0 here. This is again minus 4.667, 10.381, minus 5.714, here it is 0, minus 5.714, 5.714. So this completes our global stiffness matrix. Then again I will add the 4 degrees of freedom, Q1, Q2, Q3 and Q4. If you look at this, then this is equated to the global load vector, what you have written, that is 0 into 20 into 10 raised to 3, 10 into 10 raised to 3, and finally it is 0. See, as I told you, I cannot solve directly this equation because the matrix, global stiffness matrix being singular, that is I cannot directly take the inverse of this to find out this. This is not possible. If I want this, what I am supposed to do is, I have to take, this is the, what I can say, displacement vector. If I want to find out this, I need to inverse. I take the inversion of the global stiffness matrix. So since this is not possible, we are adding the boundary conditions. Okay. Now, what are the boundary conditions? Let us see here. If we look at the figure, the node 1 is fixed. Here, this is being the node 1, this is fixed. That means the first degree of freedom is fixed, and since this fourth node is also fixed, so obviously Q1 and Q4 are equated to 0 because since they are fixed, there is no motion, so these are 0. So as yesterday we have already discussed that as per the elimination approach, if you want to substitute these two boundary conditions into the global equation, since the first degree at the first node is going to be 0, that indicates that first row and first column need to be eliminated. So therefore, I will remove the first column and the first row. Till this, I will remove this. Similarly, since the fourth node is also fixed, so therefore, fourth row is also fixed and fourth column is also fixed. So what is left for us is, this much is left here now, and these 2 degrees of freedom are left now, and these 2 global nodes are left here. So let us rewrite this now, reduce the matrix before we solve the equations. We will take up this one. See, for example, the leftover things is now 10 raised to 5, 10 raised to 5 into bracket 12.542 minus 4.667 minus 4.667 10.381, and the 2 degrees of freedom which are left are Q2 and Q3, and the global load vectors which are there on the force vector, this is 10 raised to 3. So this is, now you will get two simultaneous equations, two linear equations you are getting. Solving them simultaneously will give you the values of these nodal displacements. So therefore, Q2, after the finding the solution, you will get Q2 comes out to be 0.02345 mm, and this comes out to be 0.2017 mm. So therefore, we have found out the 2 degrees of freedom which are possible here now. So therefore, if I want to write the total global nodal displacement, as the first node it is 0, second it is 0.02345, and third one is again 0.02017, and fourth node being fixed. Since it is a column vector, I need to write the transpose, and since the unit of all this is mm, so let us write this mm also onto this. So once we get the global nodal displacement vector, now definitely we can find out the remaining things like stresses, reactions, and all these things can be found out from this. Here as a sample, I will just give you one of the equation for the first member. In the similar way, we can find out for the second member, third member, and fourth. All these things can be found out. So let me find out the stresses in the first member. Here, for example, stresses in the first member only. Of course, you can find out for all the three members, but here I would like to show you only the sample calculation. See, for example, first member is sigma 1, and as I have already told you this is going to be what is called as stress into strain, and strain itself is given by a matrix called B, strain displacement matrix, and the nodal displacement connectivity, whatever it is there here. So according to this, what we have to write is, this is E, and this is LE, this is 1 minus 1, 1, and here we will get the corresponding element nodal connectivity, we will get that, and then I have to solve for that particular element. Let us solve it for the first member. Let us say this is the general equation, I can say. Now let us say first element, Young's modulus being 70 into 10 raised to 3 divided by 80 mm. This is that minus 1, 1. And the first element is going to be Q1 and Q2. This is for the first member it is Q1 and Q2. So therefore I will put Q1 is 0, then this is 0.02345. So if you do this, you will get the corresponding stress in the first member, 5187 megapascal. Please look here, since you are getting a positive number, it is nothing but it indicates that the first member is tensile in nature. If you go to the second member also, we may have to calculate in a similar way. I will not show you. If you calculate this, for example, this is 105 into 10 raised to 3 upon LE. LE is going to be 90. This is going to be minus 1, 1. And here you will get the next displacement Q2 is Q3. Like this you will get. And if you want the third one, you will get 200 into 10 raised to 3 divided by 70 minus 1, 1. And the last displacement is Q3 and Q4. Surprisingly, you will find for the last member, when you calculate it, you will get a compressive stress, because the last member, when it is pushed against the wall, this is getting developed with a compressive stress. So therefore, when you find the answers later on, you will definitely find out the first two being tensile in nature, whereas the third stress in the third member comes out to be compressive in nature. So please calculate these values and you can confirm it, what is exactly happening. Now, yesterday, again in the last class, I have told you how to find out the reactions at the support. If you look at the figure, since it is supported at the 2 points only, so it is enough that if we can solve only the two reactions, that is more than enough. For example, the general equation, what it says is reaction is given by KQ minus F. This will give you the reactions at all the 4 nodes. Of course, it is going to be size 4 by 1 because it is going to give you R1, R2 and R3 and R4. And this is not useful for this type of problems because we know that there are no supports at R2 and R3 are obviously going to be 0. So there is no need of. But when you are solving problems on trusses, there definitely will come across this type of equation is more helpful to us. So if you take the other method of finding, let us say R1, we are interested in only R1 and R4. In the last lecture, I have already told you, if you want to find out R1, we need to use K11 Q1 plus K12 Q2 plus K13 Q3 plus K14 Q4 minus F1. So if you use this equation, automatically you will get the reaction at the first support. So let us quickly take that. If you look at that, and similarly, if you want R4, the 4th row, which is where is going to be removed. This is 4th 42 Q2 plus K43 Q3 plus K44 Q4 minus F4. Of course, since we know that there are no forces applied at node 1 and node 4, obviously F1 and F4 are going to be obviously 0. So these are obviously 0, and you know, out of this, if you look at the global stiffness matrix, definitely you can make out K13 is 0, Q1 is 0, Q4 is 0. So these are all automatically get eliminated. See, these are all eliminated. And similarly, you also know that K14 is also 0. This is also 0. Whereas if you come here, K42 is 0, whereas this is also 0. So therefore, the equation becomes so simple because automatically if you refer to global stiffness matrix, these elements are already 0. So if you look at this here, like this and this are 0, here and here are 0. So these elements, when you look at this are 0 and this is 0 for the 4th row. These two are for the 1st row. This is 4th row. So automatically these are getting eliminated, and automatically since the first degree of freedom is 0, so Q1 is also 0 and Q4 is also 0. So when you solve these equations, what the reaction you will get is automatically you will get a minus reaction. As I told you, this comes out to be 18.467 into 10 raised to 3 Newton. And the other one, when you solve the other one, 525 into 10 raised to 3 Newton. This is what you will get. And I have already told you that the equilibrium, can say, equation is always R1 plus R4 has to be equal to F1 plus F2 plus F3, which is 20 plus 30, okay, 10, which is going to be 30 kilonewton. This is going to be that. So if you add these two, you are supposed to get minus 30 kilonewton only, you are going to get this. So this is going to be a cross check. If your calculations are perfectly okay, then automatically we will get all the, you can say, reactions to be perfectly equal. So this is the problem of elimination approach. We can say this is what you have to do this. Of course, this method you can use it for finding the reactions, then we can find out that. So please practice some more problems on this particular topic, so that in the next class I will be taking some more problems on elimination approach. Of course, today's whatever problem I have done it is on using elimination approach. Using the boundary condition has been handled by elimination approach. So yesterday we have seen that when the boundary conditions are specified, those respective rows and columns need to be eliminated, and the overall size of the global stiffness equation has to be reduced, and then it will be simple for solving those equations, and then you will get the correct answers and all that. You will be getting that. See, for solving the simultaneous equation, once you got this can also be done like this. For example, 10 raised to 5, you can keep it outside. This is 12.542 Q2 minus 4.667 Q3 is equal to 20 into 10 raised to 3. This you can take. And the second equation you can write it as minus 4.667 Q2 10.381 Q3 is equal to 10 into 10 raised to 3. So by solving these two simultaneous equations, you can solve this. See, for example, if you take this, you can anyway take this 10 raised to 5 on the right hand side. That will become 20 into 10 raised to minus 2. Similarly, you will get again 10 raised to minus 2. Once you solve this simultaneous equation, you will get the answers for Q2 and Q3. Of course, with the number of degrees of freedom, if it is more than 2, like for example, you will get 3 simultaneous equations, then if you have the provision in your calculator, then it can be solved in that particular way. If not, then by using any of the techniques like Gauss elimination method or any other Cholesky method, one can solve these equations and simultaneous equation and get the answers for Rhodol degree of freedom system. So in our next lecture, I will be taking numericals on elimination approach, some more problems, and then we will discuss about penalty approach also. Once these are completed, we will enter into the other topics. Like we will take into account the effect of temperature also. Then we will complete these problems.